Look at the below diagram. A mass M, that's this point over here, is ejected by a compressed spring. We push the mass against the spring and then let it go. It spins around a couple loops. It goes like this, comes around up here, kind of like a roller coaster. Then keeps going here, comes up to this loop, and then finally comes out at the end. We're going to assume no friction here, and we want to find the velocity of the mass at point A and point B. Could you use free body diagrams and Newton's laws to solve for this? That would be very complicated because as the mass goes around these loops here, its acceleration continually changes. And once you have a changing acceleration, you cannot use the kinematics equations. So that would be very hard. However, let's look at conservation of energy. The system will be the spring, the mass here, the block, and the two loops. We're assuming no friction, so at any point on this system, there is no work being done. Therefore, the energy at point 0, this is where the spring is compressed. Point 1, that's where the spring lets go and propels the mass. Point A and point B, the energy has to be the same at all of those points. Let's examine the energy at each one of these points. We start at E0, that's when the spring is compressed. First of all, we'll assume that this baseline here is where gravitational potential energy is 0. So at point 0, all the energy is in the spring, 1/2 k delta x squared, where delta x is how much we've compressed the spring. At point 1, the spring has released. The object is moving. We have kinetic energy, 1/2 mv1 squared. Now let's look at point A. This can be a mite tricky. We give the radius of the circle as RA. Now if that's the case, then the height from here to here is going to be twice RA. So its potential energy will be mg2r sub A, and it will be moving here, so we have a kinetic energy. And then finally we get over to point B, and it's very similar to point A, except for the subscripts. And again, make sure when you do these problems, if you're given the radius, when you find the height, you have to double the radius. Please note that we've given no numbers out yet. We're totally working with an algebraic equation with variables. This will enable us to solve the most general situation and plug numbers in later. And then if we want to redesign our spring roller coaster system, we can do that. We've already got the equations. So again, recall the total energy remains the same no matter where the block is on its journey. And here's our most general equation up here. Let's find the velocity at point A first. Okay, we could have found the velocity at point 1, but that's just right here. And that just seems, we've done that before. That's not terribly hard. You just solve that for V1. But in this case, we're going to be looking at point A. So we have 1/2 k delta x squared equals this part of the equation. This is the key equation that relates to point A. So we don't need to look at this. We don't need to look at the energy at point B. So we have 1/2 k delta x squared equals 1/2 mva squared right here, plus mg2ra. We isolate our variable VA, move her over to the left here, move 1/2 kx squared on the right. The signs change. We then multiply through by 2, divide by m, take the square root, and here we go. I know I went through that rather quickly, but this is something you can do at your desk with your own piece of paper there. And you find out that the velocity of A is the square root of k over m, x squared, where x is how much you've compressed the spring. We dropped the delta there somewhere just to save notation. Minus 4g times the radius of loop A. What else can we solve for by just changing the solution a little bit? We can use the exact same mathematics to find the velocity at point B. If you'll go back a slide, you'll notice that the energy at point B is algebraically similar to the energy at point A. We just have a different subscript. So here's VA, this is what we calculated, and I'll just write down what VB should be. Same exact variables here, and then we just change the radius from the radius of loop A to the radius of loop B. Now we put in the numbers. Remember, we only put the numbers in at the very end. And we find the velocity at point A is 8.5 meters per second, and the velocity at point B is a little less. It's 7.5 meters per second. Let's apply some physics intuition and find out, or please discuss, why the velocity at point B is less than the velocity at point A. Take a couple seconds, pause the video if you need to, and then we'll pull back the screen here. Okay, hopefully you've already worked this out with your groups. And here we go. The block has a greater gravitational potential energy at point B. So since the energy is conserved, it has a smaller kinetic energy. Hence, you have a smaller velocity. What's really nice about this is we really don't care if this is a circle, if it's an ellipse, if it's any kind of loop. All we care about is the height that it gets to,